What if I told you that everything you are, everything you've ever experienced, every memory, every thought, every atom in your body, is nothing more than information projected from a two-dimensional surface at the edge of the universe? What if the three dimensions you inhabit, the depth you perceive, the space between stars separated by trillions of miles, what if none of it is fundamentally real? In 1997, a physicist named Juan Maldacena published a paper that would shake the foundations of reality itself. His mathematics suggested something impossible, that our entire universe, with all its depth and complexity, might be a hologram. Not metaphorically, not approximately, actually a hologram. The implications are staggering, the evidence is mounting, and the most brilliant minds in physics are taking it seriously. Today, we journey through evidence that challenges everything we thought we knew about the nature of reality itself. Prepare yourselves. We begin.
In 1974, Stephen Hawking discovered something that shouldn't exist. He was studying black holes, those cosmic predators whose gravity is so intense that nothing, not even light, can escape their pull. According to Einstein's equations, black holes are deceptively simple objects. They have mass, they have spin, and they have electric charge. That's it. John Wheeler famously said, "Black holes have no hair," meaning they have no other distinguishing features. But Hawking found that black holes aren't quite so simple. By combining quantum mechanics with general relativity, he calculated that black holes actually emit radiation. They glow, very faintly, with thermal radiation. Over unimaginable stretches of time, they evaporate. This discovery created a paradox that would haunt physics for decades. Here's why. When you throw a book into a fire, the information in that book isn't destroyed. It's scrambled, transformed into ash and heat and light, but the information still exists encoded in the particles. Given perfect knowledge of every particle, you could theoretically reconstruct the book. This is a fundamental law of physics. Information cannot be destroyed. But a black hole presents a problem. When you throw that book into a black hole, it disappears beyond the event horizon, the point of no return. And if the black hole eventually evaporates through Hawking radiation, where did the information go? The radiation appears to be completely random, containing no trace of what fell in. This is the black hole information paradox. And for 20 years, it seemed unsolvable. In 1972, Jacob Bekenstein, then a graduate student, made a radical suggestion. He proposed that black holes have entropy, a measure of disorder in information content. But here's the strange part. The entropy of a black hole is proportional not to its volume, but to its surface area. Think about that. When you have a box of gas, the amount of information needed to describe it, the positions and velocities of all the molecules, depends on the volume of the box. Double the volume, double the information content. This seems obvious. It's how three-dimensional objects work. But for black holes, it's different. The information content is written on the two-dimensional event horizon, not in the three-dimensional interior. Bekenstein's formula was elegant and precise. The entropy equals 1/4 of the event horizon's area, measured in Planck units. This isn't an approximation, it's exact. At first, this seemed like a curious mathematical peculiarity. But physicist Leonard Susskind began to wonder, what if this principle applies not just to black holes, but to everything? In 1993, Susskind and Gerard 't Hooft independently proposed what they called the Holographic Principle. They argued that the maximum amount of information contained in any region of space is proportional not to the volume of that region, but to the area of its boundary. The universe, they suggested, might work like a hologram, those special images on credit cards that appear three-dimensional but are actually encoded on a two-dimensional surface. When you look at a hologram, you see depth, you see objects existing in 3 dimensions. But it's an illusion. all the information is actually stored on a flat surface. Could our universe work the same way? Could the three dimensions we experience be projections of information encoded on a distant two-dimensional boundary? It sounded like science fiction. It violated every intuition about the nature of space. Most physicists were skeptical, but then Juan Maldacena did something extraordinary. In 1997, while working at Harvard, Maldacena discovered a precise mathematical relationship between two seemingly different theories. On one side, he had a theory of quantum gravity in a particular kind of five-dimensional space called anti-de Sitter space. On the other side, he had a quantum field theory, like the theories that describe particle physics, living on the four-dimensional boundary of that space. The remarkable thing? These two theories were exactly equivalent. They were different descriptions of the same reality. Anything that happened in the five-dimensional interior could be completely described by processes on the four-dimensional boundary. The bulk was a hologram of the boundary. Maldacena's ADS/CFT correspondence, as it's called, wasn't a vague analogy. It was a precise mathematical dictionary translating between the two descriptions. Physicists could perform calculations in one theory and get exact answers in the other. For the first time, the holographic principle wasn't just philosophy, it was mathematics. But the evidence forces us to confront an uncomfortable possibility. If this works for Maldacena's special space, could it work for our universe? In 2009, physicist Mark van Ramsdonk made a startling discovery while studying Maldacena's correspondence. He found that the geometry of space itself, the very fabric of reality, emerges from quantum entanglement. Entanglement is that strange quantum phenomenon where particles become correlated in ways that Einstein called spooky action at a distance. When two particles are entangled, measuring one instantly affects the other, regardless of the distance between them. Van Ramsdonk showed that in Maldacena's holographic universe, regions of space that are connected, meaning you can travel from one to another, correspond to entangled particles on the boundary. Cut the entanglement, and space itself tears apart. This suggests something profound. Space is not fundamental. Space is an emergent phenomenon, a projection arising from the pattern of quantum entanglement among particles living on a distant boundary. Multiple research groups have confirmed these results using different mathematical approaches. In 2013, physicists at the Institute for Advanced Study demonstrated that Einstein's equations, the very laws that govern gravity and space-time, emerge naturally from the patterns of entanglement on the holographic boundary. Gravity itself might be a hologram. If the universe is holographic, there should be fundamental limits on how much information can exist in any region of space. And we found them. In 1999, Raphael Bousso at Stanford formalized what's called the covariant entropy bound. This principle states that the entropy flowing through any light sheet, a two-dimensional surface traced out by light rays, cannot exceed 1/4 of the area of that surface in Planck units. Researchers have tested this bound in numerous scenarios: black holes, cosmological horizons, quantum field theories. Every test confirms it. Nature seems to respect this fundamental limitation. The universe behaves as if information is stored on surfaces, not in volumes. But here's where it gets even stranger. In 2010, physicist Erik Verlinde at the University of Amsterdam proposed that gravity itself is not a fundamental force but an entropic phenomenon, essentially a side effect of information trying to maximize disorder on the holographic boundary. Verlinde showed that Newton's law of gravity emerges naturally from this thermodynamic perspective. You don't need to assume gravity exists. It appears automatically from the holographic distribution of information. In 2008, researchers at the GEO 600 gravitational wave detector in Germany noticed something peculiar. Their instrument was picking up unexplained noise, a persistent background hiss that shouldn't exist. The detector works by measuring the distance between mirrors, suspended kilometers apart, with extraordinary precision, accurate to 1,000th the diameter of a proton. But the mysterious noise was at just the right frequency to match a prediction made by Craig Hogan at Fermilab. Hogan had calculated that if space itself emerges from information encoded on a holographic boundary, there should be fundamental quantum jitters in the fabric of space. Holographic noise. The size of these jitters depends on the Planck length, the smallest meaningful distance in physics, approximately 10 to the negative 35th meters. The noise at GEO 600 matched the prediction. Now, this remains controversial. The GEO 600 team has not definitively confirmed holographic noise as the source, and other explanations remain possible. But the fact that unexplained noise appeared at precisely the predicted frequency was striking. More recently, experiments at Fermilab's holometer, a device specifically designed to detect holographic noise, have placed stringent limits on certain models of holographic space-time. While they haven't definitively proven the universe is a hologram, they've constrained what form such a hologram might take. But this represents just one piece of a much larger puzzle hidden in the mathematical structure of reality itself. If our universe is holographic, there's a disturbing question. Where is the boundary? In Maldacena's example, the boundary is clear. It's the edge of his anti-de Sitter space. But our universe doesn't have an obvious edge. The cosmos appears to extend infinitely in all directions, or at least curves back on itself without boundaries. However, our universe does have a boundary of sorts, the cosmic horizon. Due to the expansion of space accelerating, there's a fundamental limit to how far we can see or travel. Light from beyond approximately 16 billion light-years away will never reach us. This creates a kind of boundary, a cosmic event horizon surrounding each observer. In 2011, researchers including Thomas Banks and Willy Fischler suggested that this cosmological horizon might be the holographic screen. The information content of everything we can observe is encoded on this boundary, which has a surface area of about 10 to the power of 123 Planck areas. This means the total information content of our observable universe is finite, approximately 10 to the power of 123 bits. Everything that exists, every particle, every galaxy, every thought, must be encodable in this vast but limited number. The most remarkable discovery involves what happens when we calculate backwards. If we know the maximum information content, we can estimate the maximum entropy of the universe. And when physicists do this calculation, they get answers that match cosmological observations. The universe's entropy budget appears to be precisely what we'd expect if reality were holographic. In 2015, physicists discovered something that seemed impossible to be coincidence. The mathematical structures that appear in quantum error correction codes, the techniques used to protect quantum information in quantum computers, are identical to the structures that appear in holographic space-time. Ahmed Al-Mhairi at the Institute for Advanced Study, along with collaborators Shidong, Daniel Harlow, and others, showed that the ADS/CFT correspondence has built into it the same architecture as a quantum error correction code. Think about what this means. In a quantum computer, information is stored redundantly across multiple qubits so that even if some qubits are damaged, the information can be recovered. The code creates a kind of resilient, interconnected web of information. Holographic space-time appears to work the same way. Information about the interior of space is encoded redundantly across the boundary. You can lose access to part of the boundary and still reconstruct what's happening in the interior. This isn't just a vague similarity. The mathematics is identical. The structure of space-time geometry is mathematically equivalent to a quantum error-correcting code. Why would nature use the same information theoretic structures for quantum computing and for the fabric of reality itself? The most natural explanation. Because reality is information and space is the code protecting that information. For decades, physicists struggled to calculate the properties of quantum field theories, the theories that describe how particles interact. The equations were too complex, requiring approximations and supercomputers. But in the holographic picture, there's another way. These same theories live on the boundary of a holographic space-time. And the symmetries of that boundary place powerful constraints on what theories are possible. In the past 15 years, a technique called the conformal bootstrap has allowed physicists to calculate exact properties of quantum field theories using only their symmetries and consistency requirements. The technique doesn't require knowing anything about the interior space-time, only the structure of the boundary theory. And it works. Researchers have calculated critical exponents, correlation functions, and particle spectra with precision that matches or exceeds traditional methods. The Bootstrap program, led by physicists including David Simmons-Duffin at Caltech and Slava Rychkov at CERN, has solved problems that were intractable by other means. The success of these methods suggests that the boundary theory really is fundamental. The bulk space-time, our apparent three-dimensional reality, may be secondary, a derived quantity that emerges from the boundary dynamics. The evidence extends beyond theoretical physics into the realm of information theory, quantum mechanics, and the very structure of mathematics itself. The holographic principle forces us to reconsider fundamental assumptions about the nature of space and time. We've always thought of space-time as the stage on which physics happens, a fixed background, a container for matter and energy. Einstein taught us that this stage is dynamic, that it curves and warps in response to mass and energy. But even in Einstein's theory, space-time itself is fundamental. The holographic principle suggests otherwise. Space-time is not fundamental, it emerges. Leonard Susskind and Juan Maldacena have argued that space-time is like temperature. When you look at a gas, you perceive it has a temperature, but temperature isn't fundamental. It's a statistical property of countless molecules jiggling around. At the microscopic level, there is no temperature, only the motion of individual particles. Similarly, space-time might be a large-scale approximation of something more fundamental happening on the holographic boundary. At the deepest level, there is no space, no time, no gravity, only information and entanglement. The three dimensions we experience would be an illusion, albeit an extremely convincing one. Like the three-dimensional image that appears when you view a hologram, our spatial reality would be a projection of information encoded on a distant two-dimensional surface. This resolves the black hole information paradox. The information that falls into a black hole doesn't disappear. It's encoded on the event horizon. From the holographic perspective, nothing ever really goes inside the black hole. Everything always exists on surfaces. The holographic principle has moved from fringe speculation to mainstream physics. Thousands of papers have been written exploring its implications. It's taught in graduate courses at leading universities. Edward Witten at the Institute for Advanced Study, one of the most influential physicists of our time, has called the ADS/CFT correspondence one of the greatest discoveries in theoretical physics. Nima Arkani Hamed at the Institute for Advanced Study has gone further, suggesting that space-time itself might be doomed, that future theories of physics will abandon space-time entirely as a fundamental concept. Brian Greene at Columbia University has explored how holography could unify quantum mechanics and gravity, potentially solving the deepest problem in fundamental physics. Stephen Hawking, before his death in 2018, embraced holography as the solution to his information paradox. acknowledging that information is preserved on the event horizon of black holes. Not everyone is convinced. Some physicists argue that the holographic principle applies to special cases like black holes and anti-de Sitter space, but doesn't generalize to our universe. Others worry that the mathematics, while beautiful, might not describe physical reality. But even the skeptics acknowledge that something profound is happening here. The mathematics works too well, explains too much, to be mere coincidence. The philosophical implications are staggering. If we live in a hologram, what does that mean for consciousness, for free will, for the nature of reality itself? From the holographic perspective, every moment of your life, every decision you've made, every neuron firing in your brain, all of it is encoded on a distant boundary surface. Your experience of three-dimensional space, of moving through time, would be emergent phenomena, patterns in the information on that boundary. Are you the three-dimensional being you appear to be, or are you fundamentally a pattern of information on a two-dimensional surface, projecting the illusion of depth? Recent breakthroughs suggest we may be able to test holographic models experimentally. The next generation of gravitational wave detectors, including the space-based LISA mission planned for the 2030s, will be sensitive enough to potentially detect holographic noise in space-time itself. If space has a quantum pixel structure, as some holographic models predict, these instruments might see it. Quantum computers offer another testing ground. IBM, Google, and other companies are building quantum processors with hundreds of qubits. Researchers are using these machines to simulate holographic correspondences, creating small-scale models of holographic spacetimes in the laboratory. In 2019, physicists at Google and the University of California, Berkeley used a quantum computer to simulate a holographic wormhole, a tunnel through space-time connecting two distant regions. While the simulation was tiny, involving just 9 qubits, it demonstrated that holographic space-time can emerge from quantum entanglement in controllable experiments. Future quantum computers with thousands or millions of qubits might simulate larger holographic universes, allowing physicists to test predictions of holographic theories in unprecedented detail. The Event Horizon Telescope, which famously captured the first image of a black hole in 2019, continues to make increasingly precise observations. If holographic models make different predictions about black hole dynamics than standard theories, these observations might reveal them. If our universe is holographic, it changes how we think about cosmology, the study of the universe's origin and evolution. The Big Bang, that moment of creation 13.8 billion years ago, might not have been an explosion in space, but rather an event on the holographic boundary. The expansion of the universe would correspond to the boundary area increasing over time. Dark energy, the mysterious force accelerating cosmic expansion, might find a natural explanation in holographic models. Some physicists have proposed that dark energy emerges from the quantum entanglement structure on the holographic boundary. In 2017, researchers, including Just de Haro and Petar Pavlovich, showed that certain holographic models reproduce the observed acceleration of cosmic expansion without requiring a cosmological constant, Einstein's famous fudge factor. The cosmic microwave background radiation, that ancient light from when the universe was just 380,000 years old, contains patterns that encode information about the universe's earliest moments. Holographic models make predictions about these patterns. So far, observations from satellites like Planck are consistent with holographic scenarios, though they don't yet prove them. The holographic principle appears to resolve the black hole information paradox that troubled physicists for decades. When matter falls into a black hole, the information doesn't disappear into the interior. Instead, from the holographic perspective, everything that falls in is always on the horizon. The interior of the black hole is a holographic projection of the horizon, another description of the same degrees of freedom. Recent work by Ahmed Al-Mhairi, Netta Engelhardt, Donald Marolf, and Henry Maxfield has refined this picture through what they call the islands proposal. They showed that quantum information can be preserved through subtle correlations between Hawking radiation and the black hole interior. The information comes out scrambled in the Hawking radiation, but it does come out. The paradox is solved. This represents a triumph of holographic thinking. A problem that seemed impossible to solve using traditional approaches yields to the holographic perspective. What scientists discovered next would challenge not just our understanding of space, but of reality itself. The most profound implications emerge when we consider what holography means for the nature of existence. If you're fundamentally a pattern on a two-dimensional boundary, what does it mean to be conscious? Your thoughts, your memories, your sense of self. All of these would be information patterns on a holographic screen. Does this make consciousness less real? Or does it reveal something deeper, that consciousness is fundamentally about information processing, not about the particular substrate on which that processing occurs? From the holographic perspective, the distinction between physical and informational dissolves. Matter, energy, space-time, these are all manifestations of information on the boundary. In a very real sense, reality is information. This connects to questions philosophers have pondered for millennia. Is the universe fundamentally mental or physical? The holographic principle suggests the question is misguided. Information is more fundamental than either. John Wheeler, the physicist who mentored many holography pioneers, famously proposed it from bit, the idea that physical reality emerges from information. The holographic principle seems to vindicate his vision. Here's where things get truly strange. Some physicists believe there might be multiple valid holographic descriptions of the same reality. Different boundaries, different dimensions, all describing the same universe. This is called holographic duality. The same physics can be described by different theories living in different numbers of dimensions. There's no fact of the matter about which description is real. They're all equally valid. Imagine a book written in two languages on facing pages. The English and Spanish versions contain the same information, tell the same story. Neither is more real than the other. They're both the book. Our universe might be like that book. The three-dimensional version we experience and the two-dimensional boundary version might both be complete, accurate descriptions. Reality itself might be inherently ambiguous about its own dimensionality. This threatens the very notion of objective reality. If multiple incompatible seeming descriptions are all true, what is reality? Perhaps reality is not a thing, but a relationship. A correspondence between different descriptions, all of them valid, none of them privileged. The holographic principle connects to other radical ideas in physics, including the multiverse. In eternal inflation theory, our universe is just one bubble in an endlessly inflating multiverse. Each bubble has its own laws of physics, its own constants of nature. Some physicists, including Raphael Bousso, have explored how holography applies to the multiverse. Each bubble universe has its own holographic boundary. The reality of each universe is encoded on its boundary surface. This suggests a bizarre possibility. Perhaps the multiverse itself has a holographic structure. Perhaps there's a meta-boundary encoding all possible universes, all possible laws of physics. If true, this would mean that every possible universe, every variation of the laws of nature, every branching of quantum possibilities, exists as information on some ultimate boundary surface. Everything that could happen does happen, somewhere in the holographic multiverse. The connection to simulation theory is unavoidable. If reality is information on a holographic boundary, is there a meaningful difference between real and simulated? Both would be information processing systems. Both would be equally valid descriptions of existence. Nick Bostrom's simulation argument proposes that if advanced civilizations create many simulated realities, we're probably living in one. The holographic principle doesn't prove this, but it blurs the line between physical reality and information processing in a way that makes the question less clear-cut. Perhaps the universe isn't a simulation in a computer, but something stranger. A hologram that dreams itself into existence. Information that processes itself into experiencing itself. We began with a simple question. What if our three-dimensional universe is a hologram? The evidence we've journeyed through suggests this isn't mere speculation. The holographic principle emerges from multiple directions, from black hole thermodynamics, from quantum entanglement, from the deep mathematics of quantum field theory and gravity. The ADS/CFT correspondence provides a concrete, working example of a holographic universe. Quantum error correction reveals that space-time has the structure of an information processing system. Entropy bounds suggest information is fundamentally two-dimensional. We've learned that space might not be fundamental, but emergent. That reality might be a hologram projected from a distant boundary. That the very notion of inside and outside, here and there, might be illusions created by the pattern of quantum entanglement. The current scientific consensus remains open. Holography has proven itself in special cases and offered profound insights into quantum gravity. Whether it describes our universe remains an open question, but the mathematics is too elegant, the evidence too compelling to ignore. Perhaps the deepest lesson is philosophical. Reality might be stranger and more fluid than we ever imagined. The solid, three-dimensional world we inhabit might be a shadow cast by information living on a distant surface. This doesn't make reality less real. It reveals reality to be more subtle, more information-theoretic, more mathematical than we supposed. We are patterns in information, experiencing ourselves as three-dimensional beings in a three-dimensional space. But fundamentally, we might be something else entirely. Information processing itself, consciousness emerging from the mathematics encoded on the boundary of existence. The universe revealed by holography is one where information is more fundamental than matter, where entanglement weaves the fabric of space, where the questions, what is real and what is information, converge into a single mystery. The holographic universe isn't science fiction. It's cutting-edge physics, grounded in mathematics and tested by observation. And it suggests that reality is far stranger, far more wonderful than the three dimensions we see. The universe is vast. The mysteries are endless. The journey continues.